Hello everyone and welcome to this third video on advanced retrosynthesis. Today we will talk about alkanes, alkenes and alkynes. Especially so in this video we will talk about the use of these kind of hydrocarbons in terms of retrosynthesis. So I would like to tell you a little more on how to introduce these hydrocarbons into more complex molecules. I remind you that the best books for retrosynthesis are the two books from Warren, the disconnection approach one and the symptom one, where you can do a lot of exercises. So let's start with the synthesis and the uses of alkanes in retrosynthesis. You might think that sometimes introducing this kind of long aliphatic chains is not very useful or is not very interesting, but actually introducing them in synthesis, which is normally done via a reaction like SN1 and SN2, sometimes can be a little tricky. For instance, we can imagine starting from this halogenal alkane, a long chain, and we can use a nucleophile so that we can attack with the nucleophilic function the carbon here next to the halogen via an SN2 kind of reaction, and we can produce this kind of elongated long chain hydrocarbon. But the question now is, how can you make these nucleophiles? So for instance, we can imagine having these kind of structures. This one is actually a triglyceride, and triglycerides are quite useful for the synthesis of biodiesel. We can cut in the proper retrosynthetic approach, and we can end up having two different functions. A glycerol, which is this one, is a triol. I would like you to think about how to make it because it's an alcohol and we should know from the previous video. But the most important part for today is the synthesis of these fatty acids. So they are long chain aliphatic carbons, so all alkanes, but at the end we must have a carboxylic function. So we will see in class how can we make these carboxylic ending parts. Start thinking about any possible ideas. I would like to tell you that actually nowadays most of these kind of fatty acids are produced via enzymatic routes. So we can buy them from different catalogs, but in actual fact, for our point of view, the retrosynthesis of them is quite important. Let's see other typical ways to introduce these long chains into other compounds from the retrosynthesis and synthesis point of view. So for instance, we can remember using the Friedel-Crafts kind of reactions, especially to stick these long chains into aromatics. Remember that these kind of reactions have also some limitations. So for instance, if you start from a normal benzene ring and you want to stick this long butyl chain onto aromatic using a Friedel-Crafts alkylation, you know that instead of ending up with this kind of compound, we actually end up with a branched one. Why is that? It's always because of the migration of the one of the hydrogens in this case, which forms a much more stable carbocation, and eventually this kind of rearrangement leads to the formation of the branched product. Another limitation using Friedel-Crafts alkylation is the fact that once you introduce the first alkyl chain, this alkyl chain acts as an electrodonating group, and this always produces the possibility of polyalkylation. So we need to be very careful when using Friedel-Crafts reactions. We need to know when to stop and how to stop them. Another typical way is by using Grignard reagents. We know that Grignard reagents are very versatile reagents, and for instance, we can create a Grignard on this side and we can add it to this acyl chloride. Both of them contains really long chains, and by simple reaction we can obtain a ketone here that then eventually can be reduced down to form our aliphatic chain. Another reaction that we really need to remember, we will see especially a little later for the synthesis of alkenes, is the Wittig reaction. In this case, for the formation of alkanes, we can imagine using our phosphorus halide in the presence of an aldehyde, and then we can have our double bond in the typical Wittig way, and then of course we can reduce it down, we can reduce the double bond down to have our aliphatic chain. I would like you now to think about what kind of reagents you might use for the synthesis, for the reduction, in this case, of these two different alkyl chains to aliphatic. Let's see now the synthesis and uses of alkenes. The alkene is a much more versatile functional group. We can form alkenes, for instance, like we can see in this chart, by E2 kind of reaction starting from the correspondent halogenal compounds. We can do dehydration of alcohols using typically very strong acids, or always with alcohols. We can use different other conditions which always imply the E2 kind of reaction, so anyway elimination reactions, to form these new double bonds. Then the alkene can be used to make a different other kind of reactions. So for instance, we can do addition of water to produce new alcohols. We can use different oxidizing agents like methylchloroperbenzoic acid, for instance, to produce epoxides that, as we've seen from the previous video, can be very useful to form new alcohols. We can do hydrogenation of alkanes to form alkanes, like we can see for the previous example. We can do addition of hydrochloride or hydrobromide to form new halogenalkanes, and sometimes we can use them also for oxidative cleavage to form new carbonyl compounds. Let's see the synthesis and uses of alkanes with different practical examples. We said that probably the most common way is by dehydrating the corresponding alcohols. So for instance, let's imagine this target molecule. We have this double bond here, and we can synthesize this compound by FGIs, so starting from the alcohol, remember, and going back to the alkene is actually making an FGI, and we can have the alcohol in this position, and you can imagine having the alcohol in this position means by completing the disconnection starting from cyclohexanone and the corresponding Grignard reagent. This is a very easy reaction. We can also start from the alcohol in this position instead, so that it can dehydrate and form a double bond in the position that we want. But actually, the formation of this alcohol is more difficult than the formation of the previous one. I hope you can start thinking about it, and in class we can discuss different options. We need to be very, very careful on the position of the hydroxyl groups in terms of regiochemistry. So let's put this example instead. We have the double bond here, and we again can design two different ways to produce the double bond exactly in the position. We can start from the alcohol here, and we can imagine dehydrating that it goes there. But actually, if we remember from the chemistry of the aromatic groups, this dehydration probably will lead to the double bond in this position because it prefers to conjugate with the benzene ring. So this actual method is not viable. So we have to start from the alcohol in the further position. So we can think about, from the retrosynthesis point of view, starting from acetone and a Grignard reagent, and then eventually we can end up with the alcohol, and by dehydration we'll form the double bond in the desired position. Now, this one can dehydrate also in another different position. It's a very small amount, probably, it's a minor reaction, but I hope that you can see it. Let's see now what I consider the second most important reaction to form new substituted double bonds, the Wittig reaction. I'm sure you remember it from different other parts of the courses that you have done with me and Joel and Marcella. What I want you to remember is that you can cut in terms of retrosynthesis the double bond here, and then eventually you end up with a carbonyl part and a bromoalkane on the other side. From the synthesis point of view, just remember that the bromoalkane must be put in the presence of triphenylphosphine and bule. The bule needs to remove one of these protons, creating this negative charge. And by addition of this phosphorus halide that we just created and any carbonyl compounds, in this case acetone, we can form our double bonds. Let's see with a practical example. Let's say that we want to synthesize this double bond. We can cut it here, and we have two different options. We can form the benzaldehyde, so keeping the carbonyl on the aromatic side, and we can create the phosphorus halide on this bromoalkane. You can also form the phosphorus halide, keeping it on the aromatic side, and we can use this aldehyde instead. In this case, the phosphorus halide is created in the same way that we have seen before from the aromatic part. Now, I would like to focus also, like we said that before, on how to make this kind of compounds. So how do you make this aldehyde in the presence of this cyclohexane? We will see that in class. Let's move now to the final functional group that I would like to discuss with you today in this video, the alkynes. Especially I would like to focus on this kind of alkynes which have a proton on this end of the triple bond, which can be removed, or the kind of alkynes which have two different R groups on each side of the triple bond. Generally speaking, we can produce alkynes by a dehydrogenation or dehydration of double bonds, or in case these X's are halogens, by dehalogenation. Generally speaking, we can always use E2 kind of reactions. We can also produce alkynes by cross-coupling reactions. If you remember, we saw the Sonogashira in the first part of this course. But generally speaking, the alkynes are produced in the presence of other alkynes using various conditions. How can we use alkynes? For instance, we can use halogen to do a full halogenation up to the aliphatic part, or we can also do partial halogenation, obtaining different kind of double bonds. We can use strong bases to remove this proton here. And once this proton is removed, the alkyne becomes a very nice nucleophile that can be used to make different kind of chemistries. So alkynes can be reduced down using hydrogen up to the alkenes, so with double bonds, or up to alkanes, so with completely full reduction. We can also use alkynes to produce what is called oxidative cleavage. In this case, for instance, we can use ozonolysis to produce different kind of carbonyl compounds. Let's talk now about one of the most typical use of alkynes. As I was anticipating, in this case, by using the simplest of the alkynes, the acetylene, we can take one of these protons with a strong base, for instance with Bewley, but we can obtain the same kind of result with the Grignard, which is also a very strong base. But probably the most common one that you normally use for retrosynthesis and synthesis is this sodium amide. In all these cases, anyway, we can form the nucleophile, and the nucleophile can be used for different kind of chemistries. So, for instance, by using acetylene, in this case, and Bewley, in the presence of this halogenoalkane, we will substitute this R group on the one end of the triple bond. Or, in the presence of a carbonyl group, for instance, once this alkyne has become a good nucleophile, can attack the carbonyl, forming the typical tertiary alcohol that comes of the reaction with the ketone, with nucleophiles with ketones. Another nice reaction that we can do is, but after deprotonation of the alkyne, the attack of this epoxide, that in this case, it forms this secondary alcohol. I would like to remind you that, like we discussed for the use of epoxides in the previous video, the nucleophile here will attack the least hindered part of the epoxide. Anyway, in this case, I would like to emphasize once more that normally you produce substituted alkynes in the presence of already present triple bonds. The last reaction that I would like to show you today is the reduction of alkynes to alkenes. It's a reaction that might sound trivial, but actually, using the proper reagents and conditions, we can selectively produce different stereochemistry of the newly formed double bonds. So, for instance, using sodium with ammonia, we can preferentially form the E version of the double bond, which is the thermodynamically favored one, or by using hydrogenation with palladium over carbon poisoned with barium sulfate. If you remember, the combination of the two is called Lindlar catalyst. We can actually form the Z version of the same double bond. So, for instance, we can use acetylene in the presence of a formaldehyde and a metal catalyst, and we can form this dihydroxo compound with a triple bond here, and then by addition of the Lindlar catalyst, we can selectively form the Z compound. Let's see now with an example that might be very useful for retrosynthesis. Let's say that we want to form this diene. We know that dienes are very important for dear solder compounds, but in this case we would like to focus on the formation of the diene itself. So from the retrosynthesis point of view, we can imagine doing an FGI here, putting an hydroxyl group in this position, and then another FGI which turns this double bond into a triple bond in terms of retrosynthesis. Then of course here we can cut the triple bond and start from cyclopentanone and the acetylene. In terms of synthesis, we can simply use the acetylene in the presence of sodium amide that we saw removes one of these protons. Then we can do a nucleophilic attack on the cyclopentanone, forming the triple bond, and then by use of the Lindral catalyst we can put the double bond exactly in the position that we want. Then by simple dehydration of the alcohol here, we can form our desired diene. As a summary for this video, we can say that we saw the synthesis and their use in retrosynthesis as usual of different alkanes, especially focus on adding extra long alkyne chains into a preformed molecule. We saw the use of alkenes instead and various preparation and uses of them. And in the last part, we saw the uses of alkynes instead. Everything, as usual, has been assessed and evaluated using different examples in retrosynthesis and synthesis. Thank you for watching.